Good afternoon. So there's a lot of in the show going on about FinFETs and the latest, biggest designs. Today I want to talk a little about MCU, so microcontroller, which is maybe not the latest technology, but very interesting and very new trends there. So if you look to the IoT analog stuff, typical, you have all the world with the IoT, you have a microcontroller, and in between you have the analog IP, you have sensors, motor control. So it's a nice bridge between analog and digital. And this requires some special design consideration. You need to take care of the low power requirements. It must be very cost effective if you build millions of these designs. So the next slide simply highlight what is special here, what to consider. First of all, the area, so there's radio, microcontrollers, sensor, so a lot of integration there, which makes it a unique proposition there. Then there are some special processors, integrated non-volatile memories, EM flash, so that's important. And then you have some very unique requirements, like you need to be very energy efficient, low cost, and all this creates some interesting challenges in the design flow where you have to integrate this. If you look at a slightly different picture in terms of all the process nodes, so going 250 to FinFET, so this is the area for your application processors in your smartphones, so the very high-end stuff there. And then you have real-time DSP cores and then the embedded cores. And the interesting trend now is that the embedded IoT world covers a relatively large range in this area. So it starts with about 130 nanometer, goes down to 40 nanometer, depending on how much integration you need, how much performance you need, you can select here your process. A slightly different picture shows you on the x-axis the process progression, and on the y you see different special features from the process. So starting from top, you have high voltage BCD application, so you have directly motor control, battery monitoring, lighting. Then you have this big area, analog 6, mixed signal, touch screen, stability control, and then going more specialized processes, very low power logic, triple gate oxide logic, tire pressure sensors, body control, until you go to the embedded MCU flash, depending on your requirements, with more or less demand for flash. So you see a lot of different requirements. This is the more 90, 180, 55, 65, and then 40, 28. Very interesting, if you are like the PPA numbers, is to see the trend. That's in Cortex M0 for PPA numbers. This is normalized. It's a simple implementation using one device type. So it's not a reference design, but you see how the area goes down to a very, very small area. So you need some other stuff on the chip if you go to 28 nanometer, because there's no way to make a useful die out of this. But maybe there's a single chip solution up there, so different ways there. Cortex M0 is a very popular microcontroller from ARM. There are a lot of devices out there, from medical application to toys which are controlled this. So there's a drone which is controlled this, which you can buy. So all kinds of application. Frequency range. So these are the higher frequency ranges. A lot of application from M0 run maybe with a tenth of this or even less, because you don't need this high performance all the time. So if you look slightly different in terms of features, low cost, this is the M0. We have ultra-high density standard cell libraries, power management kit. We have some, oh sorry, I'm pressed the wrong button. We have some special compilers there, high density memory compilers, and then low power. Ultra low power doesn't mean automatically ultra low cost. So low cost and then ultra low power, you need to pay a little more for some special process or IP features, like a little more complex process. And then extended performance, Cortex M4, so that's a class better for more performance-oriented applications. And Artisan, we work with a lot of different foundries, so you have a wide selection of process nodes there. One interesting trend over the last years was with every process node you had an increase in leakage. We broke this going from 28 to 16 with FinFETs. There are no FinFETs in the older process technologies, but there are some other trends. We have this high VT options which are added on, and then there are some ULL process options, so ultra low leakage. And finally, the last and maybe most efficient way to reduce leakage is to use triple gate oxide. So that's the oxide which you typically use in the I/O area. So you build selected area of this chip with triple gate oxide. It requires also more compromises in the design flow. You have a different voltage island, so you need level shifters. But overall, if you put in the effort, you can have very low power. That's one example where ultra low power comes to a higher cost. So you need to decide by yourself what is more important, ultra low power or low cost. On the IP side, we done some development there too. We have, for example, a register file, which typically covers about the half the range, which is showed here, because then it's no longer, for larger instances, it is no longer competitive in terms of performance. So there is then an SRAM used. However, if you run 50 megahertz or 100 megahertz, performance is not an issue. So we extend the range of the register file to this larger area, have a much better area then, and then you can also save on cost there. Memory power saving modes are very complex over the last generations. There was a lot of work done in the 28 nanometer nodes, in the 40 nanometer nodes, and we done some backfill to the, let's say, older nodes, 55, 65, and you have typical active mode, standby mode, you have wake up mode, retention mode, power down modes. So with each of these modes, you save much more power. What you pay is with wake up time. So again, you have a trend and a trade-off to make between performance and low power. So this shows this in a diagram. You have the different modes there. For example, nice 55% reduction in this retention 2 mode, and you need about 7 cycles wake-up time. So a trade-off between time that you that you are active and your power savings. More general techniques for power savings, dynamic power, leakage power. It's also important to understand your application, what is more important. If you can totally shut down your device and run it in a very short burst mode, maybe dynamic power is more important as the leakage power. So select what to choose there. There's a lot of things very easy, but also backbias support, which is still a good option in these older process nodes. Retention flip-flops makes it a little more complicated in your design flow, but you can also save a lot of energy there. Finally, how do you find all this IP? You saw the slides. We have a lot of process nodes. We have a lot of foundries which we support. What we have is a design start portal. You can download evaluation IP there with a simple click-through license. So this enables you to play with the IP very early on, so no need to make a fixed decision there. And you can sort between foundry, you can sort process geometry, process node, and then the IP type. And so very effectively, you can download a library for a specific 55 nanometer process node, for example, or whatever you want. So there's, you can go directly via this design.arm.com, or you can also go to arm.com, and then there's a portal for this. We also have, for the different types of memories, a tool which we call Mem Explorer. This helps you in the area where the memories overlap in terms of size, in terms of functionality, to find the best possible memory for you. This can be best smallest area, best performance, lower power, so there are different ways to select the memories. And with the variety of memories which we have now, that's a very useful tool there. So you select here the compiler, instance size, the speed, and then you get the different inputs about the memory. Again, designs.arm.com. So summary. ARM does a lot of process support, a lot of foundry support. So you see there a lot of foundries, a lot of process nodes. For the MCU area, somewhere 130, 28 nanometer is the sweet spot. A lot of activity going on there. It's no longer the old stuff which stays behind, a lot of refresh, new developments there. And with this, I want to end. And